This is Chapter 4, Earth Materials, Lecture 2. We left off with rock or mineral cleavage, actually, and we'll pick up with the periodic table. So here's the periodic table. What you have is an arrangement from the lightest element to the heaviest. The letters are abbreviations for each element. The number you see in the top left is the atomic number, and that's your number of protons. The color represents the type of elements. Like you have the main group metals, transition metals, nonmetals, noble gases, lanthanide series, and actinide series. Now, noble gases do not readily combine with other elements, and atomic numbers higher than 92, except for plutonium, which is 94, are not known in natural settings, but they can be produced in the laboratory. And it's fundamental to this class to have some familiarity with the periodic table and elements based on the major classes of rock forming minerals or minerals that end up forming rocks. So we'll start out with silicates. Silicon and oxygen would be our most common rock forming mineral group. And then carbonates with carbon. Carbon and oxygen bond with another element to form those rocks. And then oxides would be oxygen bonded with a metal, like iron oxide. Halides, looking at chlorine or fluorine, those would be typically bonded with a metal from the left side of the periodic table. Sulfates, you'd have sulfur combined with oxygen and bonded to a metal. And then sulfides would be sulfur bonded with a metal. We can also have native minerals. That just contains a single element, like gold, silver, or copper. So we'll break those down, starting with silicate minerals. This is the silicate tetrahedron. It's one silicon atom bonded with 4 oxygen atoms. It can link together to form a variety of silicate minerals, which are relatively strong bonds. So we have these independent tetrahedra. They can be linked in various ways in silicate minerals. Independent tetrahedra do not break along clearly defined planes. Looking at olivine as an example of a silicate mineral. So we can have single chains where the silicon tetrahedra bond together to form these chains, as in pyroxene. You can have a silicate mineral with double chains where the tetrahedra bond to form those chains, as with amphibole. And then that mineral cleaves parallel to the double chains, which results in 2 planes of cleavage at 60 and at 120 degrees. So perpendicular. We can also have sheet silicates. You have the tetrahedra bonded into sheets, which might be weakly connected to one another. In the case of mica, that's true. So you end up having one plane of cleavage or breakage along that weak bond. Or you can have silicate minerals that form in frameworks. So the tetrahedra are bonded together with other elements in a 3-dimensional framework here. It's a complex lattice, and it's going to fracture instead of cleave. And that's what we have in the case of quartz. Feldspar, however, has cleavage. A couple directions of cleavage. All right, moving out of silicates, we have carbonate minerals, which can form rock. So we have calcite on top. We see that a lot in coral reefs and shells. Those would be organic. but later those materials can be consolidated into limestone, the rock. So that's calcium carbonate, or dolomite, which is calcium magnesium carbonate. It's similar to calcite. Um, it's more stable at the Earth's surface if magnesium substitutes for some of the calcium in the mineral structure and forms calcium magnesium carbonate. All right, now oxides, those could be magnetite or hematite. Magnetite is commonly found in small black grains in igneous, sedimentary, and metamorphic rocks. Hematite forms in oxidizing conditions, such as when other iron-bearing minerals oxidize. Here's some sulfide examples. Good metallic luster here with pyrite, fool's gold, that's an iron sulfide, galena, lead being the metal in there. It's mined for its lead content, and its cubic cleavage is pretty interesting to look at. And then copper sulfide, also mined for metal content. So iron, lead, copper. Halides and sulfates here. So halite is a halide. Gypsum, that's calcium sulfate with water as well contained in that. Halides formed from the evaporation of salty water. Gypsum forms similarly to halite, but it can also precipitate within veins in a larger rock as well. We expect to find different minerals in different parts of the earth. So starting with continental crust, you'll see mostly light-colored silicate minerals such as quartz or feldspar in the upper crust. With oceanic crust, you'll see more dark-colored silicate minerals and calcium-rich feldspar. In the upper mantle, you'll see dark-colored and green silicate minerals. And in the lower mantle, I don't have a good example on here, but you'll see minerals that are stable at very high pressures, such as iron, magnesium, silicates, and oxides. In the outer core, you will see molten iron with nickel and other elements. In the inner core has crystalline iron and iron-nickel alloys. So this shows you the average abundances of elements in the Earth's crust, and it's kind of like a bar chart. So oxygen is the most abundant element, represented by the tallest column here. Silicon is the second most abundant, and then aluminum. We have some abundant metals as well over here, but iron is the most abundant transition metal within the Earth's crust. For the entire Earth, the whole thing, oxygen still the most abundant element. Within the core, iron and nickel are quite abundant. And then silicon, sulfur is less abundant, but it is abundant in the core. Magnesium, a little less than silicon. Within the whole universe, hydrogen is the most abundant element. Helium is the second most abundant element. Okay. So this is a representative model of an atom. So an atom has a nucleus that's composed of protons and neutrons. And it has an area of electrons around that. Electrons occur in electron shells that can hold a certain number of electrons. So in this case, we have 2 electrons within an inner shell, and then 8 electrons in the next shell. and then 8 in the next. The outer shell electrons, or the outer electron shells, can gain or lose electrons. Gaining or losing electrons can change the atom's charge. So this atom has 7 electrons in the outer shell. It has space for one more. This atom has 1 electron in the outer shell. Atoms can bond by loaning or sharing electrons. Bonds are important in the formation of minerals. All right, so the periodic table is organized this way by electron shells. Our columns are groups. They're called groups, so we have 1 through 7. Groups can have, or groups do have, the same number of electrons in the outermost shells of their atoms, and they form bonds of the same type. The horizontal rows are called periods, and periods correspond to the relationship of orbitals, and those are areas in which electrons will be found inside the outermost shell of the atom. So as we go down these rows, or these periods, we have atoms with more electron-rich cores of inner shells. So if you look at this, you can predict how many shells each element has and how many electrons are in their outer shells. All right, let's talk about how atoms bond together. Well, one way is by sharing, and these are for covalent bonds. Those are relatively strong, as in a diamond. Okay, so we've got this $50 bill, and two different people are holding the $50 bill, and they're sharing electrons. That's a strong bond, okay? That's a covalent bond. Atoms can bond together by loaning, and we call that an ionic bond. We have one person giving the $50 bill to another person. An atom has lost or gained an electron. Because it can do that, it can do it again, and it tends to be relatively soluble in, say, water. Okay? Or we could have the free flow of electrons, like we've got all this cash being passed around in a metallic bond. Electrons are shared widely here. This money is shared widely. So the material is held together in a non-rigid way. You could also have a situation where atoms stick together with intermolecular force. It's relatively weak. That's where you have several types of weak bonds that can attract a molecule to another molecule. So this is just a pile of cash, and you can pull it apart very easily. Mica is an example of a mineral with intermolecular force. So crystal structure and bonds do make a difference. Here we have diamond, and that's a framework of strong covalent bonds sharing. And then graphite. It's also composed of carbon like diamond. Graphite has sheets of weakly connected atoms with intermolecular bonds. So that comes apart very easily versus the diamond structure, which does not. So it makes a difference what type of bond these atoms have. Water is special. Okay, so in the case of water, you have H2O, oxygen and hydrogen share an electron. The water molecule is neutral overall. But water is considered to be polar. So polarity occurs because oxygen more strongly attracts electrons than does hydrogen. Okay, so positive versus negative. And in that case, the polarity helps water dissolve other compounds. So you have sodium chloride, and that dissolves and breaks apart in a water solution because the chloride is attracted to one side and the sodium is attracted to the oxygen side. We have a strong attraction of the elements within a mineral to the polar water. Okay, this is just for fun. I'll show you some gemstones like aquamarine. It's a type of beryl. We have ruby, very strong variety of what's called corundum. We have amethyst, which is a purple variety of quartz. And then diamond, a very pure form of carbon. It's our hardest naturally occurring substance. So of course all these photos are from the book, but it just so happens that we have all these things in the state of Michigan. So this is an iron, banded iron formation. You can mine that, like in the Upper Peninsula, make steel from it. We have copper minerals, of course, that's used in wire, pipes, also from the Upper Peninsula. Calcite is a big part of cement. We have, I'll just call it limestone quarries that are used to make cement up around Alpena in the Lower Peninsula. And gypsum, mined in a few areas of the Lower Peninsula. Iosco County is a big area for this. It's mined and then wallboard is created. And we'll stop there for this chapter.